Hi everyone, my name is Bailey Chapin and this is my Physics 2212 Lab 5 called Magnetic Molasses. Let's get into the introduction. The purpose of this lab is to compare and contrast experimental and computational model of a magnet falling through a conductive tube of aluminum foil. In the experimental model, we will measure the time it takes for the magnet to fall, and in the computational model, we will use GlowScript to model the fall. Some key findings of the experiment were that the experimental model average time for the magnet to fall through the tube was 1.262 seconds, and the computational time from the model was 0.44 seconds. Now let's get into the key concepts. The first key concept is Faraday's law, which states that the integral of the dot product between an induced electric field and the length of a closed area is equal to the negative derivative of the magnetic flux. Here the magnetic flux is equal to the dot products between the magnetic field and area. This equation in the bottom right here will be used in this experiment for the change in magnetic flux over time. Other key concepts are the magnetic force on a wire loop. In this top equation, the magnetic force in the wire loop is equivalent to the cross product of the current multiplied by the L vector with the magnetic field, where the L vector has a magnitude equal to the length of the wire. When we're considering the magnetic force on a loop, the second equation here is derived. We will also be looking at Newton's third and second law, where the magnitude of the magnetic force on the loop is equal and opposite to the magnitude of the force by the loop. We will also look at Ohm's law, which relates current to voltage and resistance. Now let's get into the procedure. The system here is the falling magnet, and the surroundings are the aluminum foil tube and the earth. Some assumptions here is that we can neglect air resistance and that the only forces acting on the magnet are the force of gravity in the negative y direction and the magnetic force of the loop, or from the loop, in the positive y direction. We're also assuming that the magnet falls north pole down. Here are some of the measurements from our experimental results. The mass of the magnet was found to be 0.025 kilograms, the length and the width were found to be 0.3 meters and 0.006 meters, and the inner radius of the tube was found to be 0.0245. We used the mu from the magnet from Lab 3, which was 4.71 amperes squared. The average time for the magnet to fall through the loop based on these 5 trials was 1.262 seconds. Now we can get into the procedure for the computational model. Some of the physical constants are listed at the top, and the experimental measurements are also inputted for the tube and the magnet. You also notice that the initial condition for the velocity of the bar magnet was 0, 0, 0 at time 0. Here's the part of the computational model where we inputted the magnetic field and the magnetic flux. The equation for the magnetic field was from the Biot-Savart law, and the equation for the magnetic flux was the one derived from the initial fundamental concepts discussed at the beginning of the video. Finally, we are getting into the simulation loop of the computational model. This set of code is where we inputted the line to calculate the gravitational force on the magnet. Lastly, for the simulation loop part 2, we edited the code to calculate the net force on the magnet and also updated the magnet's velocity and position while plotting a graph of the velocity versus time as the magnet drops. Here are the results of the computational model. Using the mu of the magnet from Lab 3, which was 4.71 amps squared, the computational time in seconds was 0.44 for the amount of time it took from the magnet to fall through the tube. Here are a few more of the computational model results. With some trial and error, I was able to find the hypothetical mu of the magnet to match the experimental time in seconds, which was 1.265 seconds from the experimental procedure. With a hypothetical mu of 8.5, the computational model predicted that the magnet would fall through the tube in 1.265 seconds. Now let's get into the discussion and sources of error. The time through the tube was quite different using the mu of the magnet from Lab 3 and the hypothetical mu of the magnet based on the computational model. Again, the difference in the mu was 4.71 amps squared and 8.5 amps squared. Now, some possible sources of error are the incorrect calculation of mu from Lab 3, contact of the magnet with the tube, air resistance, which we agreed was negligible, and the measurement error of both the time and tube measurements. Now for the what if question. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Virtually zero resistivity would mean virtually zero resistance. Due to Ohm's law, zero resistance would lead to a large induced current as the current is inversely proportional to resistivity. Due to Newton's third law, the increased current and therefore increased magnetic field on the magnet would have a larger opposite force of equal magnitude and therefore causing the magnet to fall slower through the tube. Lastly, for the last what if question, what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? The holes or slots would disrupt the rings of induced current along the tube as the magnet falls. This would decrease the induced current and therefore decrease both the magnetic force on and by the loop, according to Newton's third law. This would overall cause the magnet to fall faster through the tube because the net force on the magnet is much less than the force of gravity. Thank you.